Hello and welcome back to video 5 of too many of our Prepress review at the end of our Fullerton College Prepress class semester. When we last left our heroes, we were talking about additive color and how additive color beams the wavelengths of light that your eyeball is most sensitive to directly into the eyeball, rather than letting it naturally see the world around it and see what colors are kind of visible in the world. It beams the colors your brain is looking for straight into your brain through your eyeballs. Isn't that great? Anyways, so RGB is actually how the human vision system works. That's how we're wired and how we interpret the colors that we see. Subtractive color mimics the real world a bit more closely in a way, because in the real world, the colors we see when we look around us are what's left over. We're seeing leftovers all the time, not just in my fridge, but everywhere, leftovers. Really got to stop recording when I'm hungry. Anyways, you see the sun, we'll just talk about outside for a moment. You see sunlight. Maybe it's been filtered through clouds, maybe it's not. But the sun gives us its light. That light hits everything in its path, and then everything reflects it off. Some things reflect more than others. Some things reflect more color than others. The sun comes down with what we consider full spectrum light. It has the whole rainbow within sunlight. And when it lands on that red rose we talked about last time, the red part of the rose absorbs the green light and the blue light and only reflects red light. So all we see is the light that comes off of that is red. Meanwhile, the stem supporting the rose, assuming it's a healthy plant, absorbs the red light and the blue light, and you're only seeing green. So that's where you gain the green stems and the red roses. It's the sunlight minus the parts you don't want to see. So you might notice it's kind of the inverse, not even really inverse. I mean, in the middle is backwards. You start with white when you're talking subtractive. You start with all the colors of your light source and you remove the parts you don't want to see. If you want to think about it as another fun metaphor, let's go kind of sculpty visual. If you are working in additive color, you start with nothing and you build up. That's like building something out of Legos. You take pieces, you add them to a blank spot in front of you, and when you're done, you've constructed something. I guess I could have done more of a woodworking thing. Let's scrap Legos, though I like them. Say you built a chair by taking bits of lumber and sticking them together until it's chair height and you can sit on it. But subtractive color takes a huge log. It's like those chainsaw arts, which I have mixed feelings about, where you take a tree that you cut down and you cut out parts until it looks like a bear or something. Or you can still make a chair by cutting pieces away, and what's left over is what you sit on. So that's subtractive color. That's what's happening with the light. Additive, you start with darkness and you add light until you get what you want. Subtractive color, you start with a light source and you remove the parts you don't want to see. The primary colors from additive are secondary colors or mixed colors in subtractive, and vice versa. So subtractive color is cyan, magenta, and yellow as its primary colors, and red, green, and blue are mixed. So they are kind of inverse and opposite from each other. And the difficulty of working between the two is, well, one, we have to because our computers all work in RGB because that's how it shows us things. But printers by nature must work in CMY because they can't not. They're subtractive. Unless you print on glowing paper that glows and gives you this other color, it's just not going to do it. So cyan, magenta, and yellow remove things. In fact, if you look at subtractive color, and thank you to Mr. Hirth from our 101 class on campus, he showed me this particular trick. If you look at the color circle diagram like this one, whatever color is directly opposite the middle in a subtractive color diagram is what it removes. Cyan is not just a color, it's the absence of red. Magenta is not just magenta pigment, it's when there's no green, you see magenta. And blue and yellow are opposite each other. When you see yellow, it's because you're seeing red and green light, but no blue light. So it removes the blue. Yellow gets rid of blue, cyan gets rid of red, magenta gets rid of green, and if you get rid of all of it, you end up with darkness again. Color separation. So when you use a digital camera, it takes 3 pictures at a time and puts them together into one picture for you. That's right, 3 pictures. It shoots all the red light that it sees, all the green light that it sees, and all the blue light that it sees, and it shoots a black and white image of yes or no of each, or I guess not really yes or no, of grayscale, of levels of brightness, how light or dark is the red light that I'm seeing? How light or dark is the green light that I'm seeing? How light or dark is the blue light that I'm seeing? And then it maps the three of those images on top of each other to look like a color image for you. I just pointed at you, but you didn't see it. Anyways, now let's talk about converting. This gets converted by the inverse. Let's go back to our diagram circle for a moment to make subtractive color. So we want to print red, the red light. I know you mix magenta and yellow to make red when you're mixing CMY colors, but the cyan ink controls how much of the red. So if you take the lightest parts of the red in the red thing here, that becomes the darkest part or the least amount of ink of the cyan. And the darker parts here of the red become more bright cyan. So the red channel here, if you print this as cyan, will filter out the correct color. Same goes for green and blue. The blue limits the amount of yellow you see. Or sorry, yellow will be printed on that, on all the dark spots. And actually that works out. That's how that works. However, yet again, we're dealing with theory versus the real world. While these color theories are all fine and dandy and actually do a pretty good job of explaining things, they fall short of actual practical implementation. So let's look at that for a moment. Cyan plus magenta plus yellow should equal black. If you filter out all the red light, all the green light, and all the blue light, you should be left with no light. However, the pigments we print, the papers we use, the inks that aren't quite dense enough, they fall short. They don't do it. They're not able to print with three colors. Asterisk. I believe the HP Indigo press is capable of doing this because they have such expensive, high quality inks that can handle that. I've seen them do 3-color printing instead of 4, and it actually look almost the same as 4-color printing. That's because they're using premium, extremely high-end, custom-made inks with high density pigment in them. Anyways, normal ink run on offset presses typically, and most other things out there, doesn't have the ink strength to fully remove all the color. So cyan plus magenta plus yellow should equal black, but it really ends up being somewhere like an 80% gray. Not dark enough to really give you the tonal differences you're looking for. And if you remember any of my other soapboxes, remember that the human vision system, although we're very concerned with printing the right colors, we are not that sensitive to color as a species. We are very sensitive to light to dark differences. We look for a strong light to dark contrast to determine the edge of an object we're looking at. That's why camouflage always has dark colors running through it at weird angles, why things like zebras actually kind of work. Even though everything is black and white, how does that blend in with like a yellow grassy savanna? Well, it breaks up the outline. The contrast within the zebra is greater than the contrast between the zebra and the ground behind it. And so you don't really see it as one object. It doesn't make it invisible, but it tricks your visual recognition system and breaks out the outline. Another fun one for you guys to look at, talking about this sort of weirdness, is there's an old naval camouflage called Dazzle Camo. Look it up. They attempted this in World War I and II on battleships and more importantly, container ships that would take supplies across the ocean to the battles. Anyways, you paint with these weird shapes, these weird angles, and you try to look at that through like a submarine's periscope, and you can't make head or tails of what you're looking at. It's not invisible, but it makes recognition difficult. You can't tell the type of the ship. You can't tell the direction it's going, all because you've broken up the outline with light to dark contrast. Anyway, sorry. This is supposed to be a review, and here I am going on a tangent about battleship camouflage. In case you're wondering, yes, this is indeed Ben Hewitt. You're listening to me. That's my kind of tangent. So how do you make black? Cyan plus magenta plus yellow should be black. It's not. We need black to get the tonal differences to really show proper imagery to people. How do you make the call? There's no fourth color of light that you're getting with the camera. So what it's doing is two different things. Undercolor removal, UCR, is one method of black generation. What that does is say wherever all 4 colors are going to be there, wherever cyan plus magenta plus yellow are all going to be there at full density or close to, let's add black. Clearly, if the picture shows cyan, magenta, and yellow all at 100% fully down there, it's trying to remove the color. So let's just give it a little Give it a boost, help it climb up over that wall there. Add a little bit of black, make it darker. And that's the kind of the older version of doing this. And it really only adds black to the dark, shadowy parts of the image, and it does not change other colors. It's just there to give it the extra boost and make sure that the dark parts of your image are dark enough to really show as an image. However, it has a cousin. I don't really want to call it an evil twin, but the other way of doing it is called gray component replacement. GCR instead of UCR. Gray component replacement is very different from undercolor removal. In undercolor removal, all you're doing is adding black where you need it. Gray component replacement says, well, we've got this theory here that says cyan plus magenta plus yellow equals black. So why don't we take advantage of that, and we can print this job faster, easier, and cheaper by replacing things that would have been black with black. So gray component replacement starts with the most minimum application. Says, look, if there's going to be black on the page, why are we bothering printing these other three colors? It's going to make it darker, but not by much. We can save a lot of time and money, and it'll save us issues of putting too much ink on the paper. If you have an area on the paper that's full color for all four ink colors, you could run the risk of tearing your paper, it not drying, pages gluing together when they're stacked, all sorts of problems. So one of the ways of limiting total ink coverage is to say, well, it was going to be black anyways, so why not just let it be black and get rid of the other stuff? Let's just replace it. But it goes a step further. If you're going to replace the parts that are all the way black, why not replace the parts that are sort of black? So if cyan plus magenta plus black, bad llama, let me redo that. If cyan plus yellow plus magenta equals black, well then half of cyan, half of magenta, and half of yellow equals gray. And what if we replaced that as well? What if we took that 50% middle gray that would have been about half of each of the colors and replace it with 50% black instead? In practice, it works pretty well, actually. And that's a way. And so if you do a more aggressive gray component replacement, you're telling your computer, it's okay, you know, wherever it can be substituted, substitute it. Go ahead, make the substitutions. You can change it out, it's fine. Sometimes this works. Food analogy time. Let's talk about coffee. One of my addictions. The other one is tea, by the way. I think I like caffeine. Anyways, so coffee. Typically speaking, people my level of manliness and less, sure, some people drink it black and add diesel fuel and all that good stuff. But for those of us who like it a little bit more civilized, we'll take our coffee and we'll add cream and sugar and maybe some flavor sometimes. For argument's sake, let's say it's vanilla. So you want to add cream and sugar and vanilla flavor, you can make yourself kind of a latte, and it's great. Or you could use a scoop of vanilla ice cream. What's vanilla ice cream? Why? Depending on the exact contents, and I know I'm simplifying a little here, you've got milk, cream, sugar, and vanilla flavoring. And it's cold, it's gonna cool off your coffee a little, but take that scoop of vanilla ice cream, plop it in your coffee cup, and you have yourself the same kind of experience as you would have had if you put the other stuff in. And yeah, that should work, right? Right? It kind of does. However, let's go to a less great one. Let's say you're trying to bake a cake. And a cake ingredients, if you're making it from scratch, I know there's the box options, but if you're making a cake from scratch, you want like flour and eggs and butter and sugar. And that's actually, I think, the basics of it. And maybe some rising agent, like some baking powder or something. So you don't have, you're missing eggs and sugar. But you realize, hey, I've got marshmallows. Marshmallows are basically egg and sugar, right? So I'll just use marshmallows instead of the egg and the sugar. And that'll bake a fluffy, nice birthday cake. No problem, right? The ingredients are the same. It doesn't quite work all the time. Sometimes gray component replacement is a poor substitute. Sometimes it doesn't quite work. In some cases, it works great, but in some other parts, it can cause issues by losing the identity of the color. Things like very dark browns, you'll lose the identity. It won't be a dark brown anymore. It'll just turn to black. And in some of the lighter colors, when it starts looking a little bit grayed out, it will turn it to just pure gray, and you'll lose some of the complexity of an image. You can kind of drain the life out of a photo. So needs to be used with a grain of salt. We're going to stop here and come back at the next slide and the next time. Thanks for listening.